Space is filled with explosions, brighter than galaxies, stars tearing themselves apart, black holes feeding, planets colliding, and shock waves racing across light years of emptiness. And yet, if you were there, close enough to witness all of it, the universe would give you almost nothing to hear. One of the most violent places imaginable is, to human ears, almost completely silent. That feels wrong the first time you really let it sink in. And that is exactly why this matters. Because the reason space has no sound at all is not just a trivia fact. It is a doorway into what sound really is, what space really is, and why the cosmos behaves in ways our Earth-built instincts are not prepared for. By the end, you will not just know that space is silent. You will understand where that silence breaks, and why the truth is stranger than the simple phrase makes it seem. And if you genuinely enjoy space stories told this way, with mystery first, and then the science underneath, take a second to like the video and subscribe. It really does help the channel, and it helps me keep making deep dives like this. Also, leave a comment saying where you are watching from, and tell me this: if you could hear one real sound from space safely and clearly, what would you choose to hear? A rocket launch from orbit, Saturn's rings, the sun, or something even stranger? Now imagine the scene. You are drifting outside a spacecraft, far from Earth, with the stars fixed like cold points in every direction, and a planet hanging below you in absolute black. Somewhere nearby, a metal panel slams shut. A thruster fires. A warning light flashes. Would you hear the bang of the panel? The roar of the thruster? If a meteor hit the hull a few meters away, would there be a sharp crack, a dull thud, or nothing at all? If a star exploded across the galaxy, releasing more energy in a moment than our sun will in its entire lifetime, why would the universe not carry that event to you as sound? And if space is silent, why do scientists sometimes talk about listening to the cosmos? To answer that, we have to start with something so familiar that it usually becomes invisible to us. Sound on Earth feels effortless. You speak, and your voice reaches someone across a room. A car passes outside, and even through walls, some of that noise still finds you. Thunder rolls from miles away. Music vibrates through the floor. We move through a world that constantly presses on our ears, and because it is always happening, it is easy to imagine sound as something that simply exists on its own, like light. But sound is not like light. Sound is not a thing that travels through emptiness by itself. Sound is a disturbance moving through matter. That is the first real key. Sound needs a medium. It needs something to push on. When you clap your hands, you are not sending some free-floating object into the room. You are compressing the air. The molecules closest to your hands get shoved together, then they push on neighboring molecules, and then those push on the next ones, and so on, like a chain of tiny bumps passing the disturbance forward. Your ear does not receive the original clap itself. It receives a pattern of pressure changes in the air. Those pressure changes make your eardrum vibrate. Tiny bones in the ear pass those vibrations inward. Hair cells in the inner ear turn them into electrical signals. Your brain reads that pattern and says, "Clap." That same basic process is behind speech, music, wind, barking dogs, creaking doors, jet engines, and the crash of waves. In every case, something is vibrating, and that vibration is being carried through a material, usually air, sometimes water, sometimes solid ground, which is why you can hear a train through the rails before you hear it clearly through the air. Solids, liquids, and gases can all carry sound, because all of them contain particles that can transfer those pressure changes. Now remove the material. Remove the air. Remove the water. Remove the wall, the floor, the steel beam, and spread the particles so far apart that there is almost nothing there. The chain breaks. There are no nearby molecules to bump, compress, and pass the disturbance along. No pressure wave can travel. No sound reaches your ear. That is why space has no sound at all, at least not in the ordinary way humans mean it. Space is not truly perfect nothingness, but it is so close to empty, on human scales, that for sound it may as well be. Between the planets, between the stars, between the galaxies, the average density of matter is astonishingly low. There are particles out there, yes. There is gas, dust, plasma, radiation, magnetic fields, and more. But the particles are so spread out that the conditions needed for ordinary sound transmission are mostly absent. Think of sound as a message passed from person to person in a tightly packed crowd. On Earth, the crowd is dense enough that the message can move quickly down the line. In space, the crowd has been stretched over continents. One person shouts, but the next person is so far away that the chain never forms. The message does not travel as sound. This is also why the silence of space is not a poetic exaggeration. It is a physical consequence of the environment itself. The vacuum, or near vacuum, is not simply dark and cold. It is acoustically hostile. It refuses to carry the kinds of vibrations our ears evolved to detect. And that brings us to one of the most common images in science fiction. Two starfighters streak past each other. Lasers flash. Engines roar. There is a deafening explosion as one vehicle breaks apart against a backdrop of stars. It is thrilling. It is memorable. It is also wrong, at least from the perspective of an observer floating outside in open space. Those sounds are there for us, the audience, because our brains expect them. Silence on screen often feels uncanny, even eerie, unless it is used very deliberately. But physics does not care about cinematic expectation. In actual open space, a giant explosion would bloom in light and debris and heat, and unless you were physically connected to a vibrating surface that transmitted the motion to you, your ears would get nothing. That does not mean you would experience nothing. Far from it. If you were close enough to an explosion in space, sound would be the least of your problems. The blast could flood you with radiation, tear through your suit with high-speed fragments, or unleash intense heating. In an atmosphere, an explosion creates a shock wave in the air that slams into you as sound and force. In vacuum, there is no air shock wave to carry that effect. But the energy is still real. It is just delivered differently. This distinction matters because our intuition is so strongly tied to life on Earth. We are surrounded by air. We are shaped by it. Air cushions impacts, carries smells, supports flight, scatters sunlight into blue skies, and constantly carries sound. We think in atmospheric terms without even noticing. Space strips that away. In space, many familiar effects vanish, and others become more dangerous because there is no atmosphere to soften or distribute them. Heat behaves differently. Motion behaves differently. Sound disappears. To feel how strange that is, it helps to compare sound and light directly. Light is electromagnetic radiation. It does not need matter to move through. It can travel through vacuum. That is why sunlight crosses about 150 million kilometers of space to reach Earth. It leaves the sun, races through the near-empty gap between us, and arrives 8 minutes later. Starlight does the same over distances so enormous that even years become a small unit. Light can cross emptiness because it is not a pressure wave in matter. It is a self-propagating electromagnetic disturbance. Sound is mechanical. It is literally motion in a substance. No substance, no ordinary sound. That one difference changes everything. It means the universe reaches us primarily through light, not through sound. When we look at a nebula, a galaxy, or an exploding star, we are receiving photons, or not acoustic waves. Telescopes are, in a sense, our eyes extended across the cosmos. They gather forms of light that human eyes cannot see directly, from radio waves to infrared, visible light, ultraviolet, X-rays, and gamma rays. Every part of that spectrum tells a different part of the story. But none of it is sound in the way your ears understand sound. And yet people often hear phrases like the sounds of space, songs of the planets, the roar of a black hole, or the hum of the early universe. Are those just misleading headlines? Sometimes, yes, but not always. The deeper truth is more interesting. Space is mostly silent to ears, but not every environment in the universe is an empty vacuum, and not every signal scientists call sound is meant literally. Once you understand those 2 points, the whole subject opens up. First, when there are places in space where matter is present densely enough for pressure waves to exist. Not ordinary open vacuum between stars, but gas clouds, planetary atmospheres, the plasma inside stars, the hot gas in galaxy clusters. In those environments, something very much like sound can travel. It might not be something a human standing there could hear, because the pitch could be far too low or far too high, or the environment itself would kill you instantly. But pressure waves can absolutely exist. Second, scientists often convert data into sound. This is called sonification. A telescope measures radiation, particle flows, magnetic oscillations, or other patterns, and those data are translated into audio frequencies humans can hear. This is not fake in the sense of being invented from nothing. It is a representation. Quant. It is a way of turning patterns into a sensory form we are good at noticing. You are not literally hearing the vacuum of space the way you hear rain on a window, but you may be hearing a meaningful translation of real cosmic behavior. So when we say space has no sound at all, we need one careful correction. Open space, the near vacuum between major objects, does not carry ordinary sound to human ears. But the universe as a whole contains regions where pressure waves exist, and it contains countless phenomena that can be mapped into audio. The silence is real, but it is not simple. Let us stay with the basic physics a little longer, because this is where the mystery becomes solid. The reason sound needs a medium is rooted in how waves work. There are many kinds of waves. Some, like light, are electromagnetic. Others are mechanical. A mechanical wave depends on the motion of particles in a material. Imagine a long line of people standing shoulder to shoulder. If the first person leans forward and bumps the next, and that one bumps the next, the disturbance travels down the line even though each person only moves a little. That is a rough picture of a sound wave moving through air. Areas of compression and rarefaction, crowded and less crowded molecules, propagate outward. In a gas, those molecules are already moving around wildly. Temperature is really just a measure of how much random motion they have on average. But randomness is not the same as organized wave motion. For sound to travel, the particles must be close enough together that a local compression can influence neighboring particles quickly and continuously. In the vacuum of space, the distances are too large. A molecule may travel a long way before hitting another. The coordinated handoff needed for a pressure wave breaks down. There is a useful term here: mean free path. That is the average distance a particle travels before colliding with another particle. In Earth's atmosphere near sea level, the mean free path is tiny. Molecules are packed together compared with cosmic standards. In much of space, the mean free path becomes enormous. Once collisions become too infrequent, the idea of sound as a smoothly traveling pressure wave stops making sense in the everyday way we know it. This is one of those cases where emptiness is not just the absence of things. It is the presence of a radically different physical regime. On Earth, fluids like air and water behave continuously on our scales. In deep space, and the sparse gas becomes almost ghost-like. The usual rules of touch, friction, drag, and sound transmission weaken or vanish. That has very practical consequences for astronauts and spacecraft. If two astronauts float outside the International Space Station and one taps the other's helmet with a wrench, there is no air between them to carry the sound from helmet to helmet. But if one astronaut bangs on a metal handrail attached to the station, and the other is holding that structure, vibrations can travel through the solid metal and then through the suit and body. So the event may still be felt or even heard indirectly. Sound has not become magic. It still follows matter. It just takes a different path. Inside a spacecraft, of course, sound returns. There is air in the cabin. Fans whir, pumps hum, equipment clicks. Astronauts talk, laugh, and cough, and complain about alarms, just like people in any sealed environment. In fact, spacecraft are often surprisingly noisy places internally, because life support systems, ventilation, electronics, and moving equipment all create sound. The silence of space is outside. Inside the pressurized habitat, the old familiar physics comes back. This contrast can be startling to imagine. On one side of a hull, only a few centimeters thick, there may be complete external silence. On the other side, a busy mechanical ecosystem of breathing, buzzing, circulating air, and human conversation. A thin wall separates acoustic life from acoustic void. And if that wall is breached, sound itself becomes a clue to survival. Movies often portray explosive decompression as a violent, roaring event with bodies being sucked instantly into space. Reality is more nuanced and depends heavily on the size of the breach and the spacecraft conditions. If a significant leak occurs, air inside will rush out. That moving air creates sound inside the cabin. Astronauts might hear hissing, rushing, alarms, the sudden change in the environment around them. But outside, again, there is no atmosphere to hear that rush. The noise belongs to the pressurized side. silence waits just beyond it. This is why the phrase "no sound in space" can be slightly misleading if taken too broadly. It does not mean no object in space can ever produce vibration. It means there is usually no surrounding medium to deliver that vibration as airborne sound across open vacuum. A ringing bell in a jar will go quiet as the air is removed. Not because the bell stops vibrating, but because fewer and fewer molecules remain to carry its motion outward. Space is the ultimate version of that demonstration. You may have seen some version of this experiment. A bell or buzzer rings inside a glass chamber. At first, it sounds normal. Then a pump removes the air. The object visibly continues to vibrate, but the sound fades dramatically. What changed was not the source. It was the path. Without enough gas inside the chamber, the vibrations could no longer reach your ears effectively. That is the simplest tabletop glimpse of the silence between the stars. But now the topic gets richer, because some parts of the universe are not empty enough to be silent. In fact, some are thick with gas. Take a planet with an atmosphere. If you stood on Mars, Venus, Titan, or Earth, and sound could exist, because each of those worlds has an envelope of gas around it. The experience would not be the same on each world, because sound depends on the properties of the medium. Density, temperature, composition, and pressure all matter. Sound speed changes. The way high and low frequencies travel changes. The way voices would seem to you would change too. On Earth, at room temperature, sound moves through air at roughly 343 meters per second. In water it moves much faster, and in many solids faster still, because the particles are more tightly connected and can pass the disturbance along more effectively. But on other planets, the details get strange. Mars, for example, has a very thin atmosphere, mostly carbon dioxide, with much lower pressure than Earth. SOS, NASA's Perseverance rover, actually carried microphones and recorded real sounds on Mars. Those recordings are extraordinary, not because they are loud and dramatic, but because they are so alien in their subtlety. The Martian wind is thinner, softer, more fragile sounding. Ingenuity's rotor blades, when recorded from a distance, produce a faint, insect-like buzz in an atmosphere so sparse it almost refuses the sound. Even more interesting, sound on Mars does not behave exactly as it does on Earth. The thin carbon dioxide atmosphere affects different frequencies differently, and the speed of sound varies enough with pitch that low and high tones can separate slightly over distance. A voice there would not sound quite like a voice here. That detail alone reveals something beautiful. Sound is not one universal experience. It is local. It is environmental. It belongs to the medium carrying it. Venus offers the opposite extreme. Its atmosphere is crushingly dense and hot. Near the surface, the air pressure is so enormous that a human could not survive, and the heat is hot enough to melt lead. But sound there would travel through that thick carbon dioxide atmosphere in a very different way than on Earth. The dense air would carry pressure waves efficiently. A person somehow protected, there might experience an acoustic world that feels heavy, deep, and oppressive. The same clap or shout would not live in the air the way it does here. Then there is Titan, Saturn's largest moon, wrapped in a thick nitrogen-rich atmosphere with methane and hydrocarbons drifting through a dim orange haze. Titan is colder than any place most human imagination naturally visits. Yet, acoustically, it might be surprisingly rich. If you spoke there in a suit, your voice, if transmitted through the outside air, would move through a medium unlike Earth's, but still very much present. Wind, rain of liquid methane, perhaps the slosh of hydrocarbon waves on distant lakes, all of it would create a soundscape. Space as a whole may be mostly silent, but many worlds within it are not. The sun is another case that seems to break the rule until you look closely. People sometimes say the sun is silent, and that is true from Earth across space. No sound wave crosses the vacuum from the solar surface to your ears. But inside the sun, pressure waves are constantly moving. The sun rings with internal oscillations. It vibrates in many modes, like an unimaginably vast, resonant sphere of plasma. Scientists study these oscillations in a field called helioseismology. By observing tiny ripples and motions on the sun's surface, they can learn about its interior structure, almost like doing an ultrasound on a star. This is astonishing if you pause on it. The sun, that blinding disk above us, is not just shining, it is ringing, not audibly across space, but physically, internally, as waves move through its plasma. If your ears could somehow exist safely in that environment, and if the frequencies were shifted into a human range, the sun would not be quiet at all. It would be a turbulent, convulsing ocean of pressure and motion. Stars in general can do this. Entire stars can pulsate. Their outer layers expand and contract. Waves move through them. Some stars brighten and dim in rhythms tied to internal oscillations. In that sense, the universe is full of objects that are making something like sound all the time. We just do not hear them directly, because the message does not cross the vacuum between us and them as sound. This distinction becomes even more dramatic with giant cosmic structures. Galaxy clusters, for example, contain vast amounts of extremely hot gas between their galaxies. That gas is thin by earthly standards, but spread across such enormous regions that it behaves as a medium. In 2003, astronomers identified pressure waves rippling through the gas in the Perseus galaxy cluster, generated by activity near its central supermassive black hole. This was widely described as the sound of a black hole. Strictly speaking, black holes themselves do not make sound in vacuum the way a speaker does in air, and certainly nothing like a human ear could survive there. But the phrase was pointing to something real. Pressure waves were traveling through the cluster's gas. The pitch of those waves, however, was absurdly low, far below human hearing. Human hearing ranges roughly from 20 Hz to 20,000 Hz under ideal conditions, though that range narrows with age. The Perseus cluster wave was many octaves below even the lowest note a person can hear, more like a cosmic groan stretched over spans of time and space that defeat normal intuition. Scientists mapped or shifted the frequencies upward so we could experience an audio version. Again, not fiction, but translation. That idea of translation is essential in astronomy. We often cannot experience cosmic events directly in their native form. They occur in wavelengths we cannot see, timescales we cannot sense, energy ranges that would kill us, or frequencies outside human perception. Science extends our senses through instruments and then often re-expresses the data in forms we can grasp. A false color nebula image is still telling the truth, even though your eye would not naturally see it that way. A sonified black hole waveform can be truthful too, if it is presented honestly as a conversion rather than literal sound in vacuum. And this brings us to another famous kind of cosmic signal that people sometimes describe as hearing the universe: gravitational waves. When massive objects like black holes or neutron stars spiral into each other and merge, they can send ripples through space-time itself. These are not sound waves. They do not travel through air or gas. They are distortions in the geometry of space-time, moving outward at the speed of light. Instruments like LIGO detect these incredibly tiny stretching and squeezing effects here on Earth. When the signals are shifted into the audio range, they produce a short chirp. That chirp became one of the most important sounds in modern science, even though it was not a sound wave in the ordinary sense. It was a data representation of space-time ringing. This is where language can mislead and inspire at the same time. We say the universe speaks, sings, hums, roars. Physically, those words are often imprecise. Emotionally, they point towards something real. The cosmos is dynamic, structured, rhythmic, and detectable. There are patterns everywhere. Whether we receive them as light, radio waves, particle counts, seismic ripples, or converted audio, the universe is not mute in the broad sense, or it is just not delivering pressure waves across empty space to your eardrums. Maybe the strangest part is how much our brains resist this. We are so used to linking violent motion with noise that a silent explosion feels almost impossible to imagine. Picture a massive asteroid striking the moon. On Earth, an impact on that scale would be thunderous. There would be the initial blast, the shock wave, the rumbling ground, the screaming air, debris raining down, structures collapsing, a deep pressure you would feel in your chest. On the moon, there is no substantial atmosphere. If you watched from nearby in a suit connected only to your own life support and not physically coupled to the ground, you would see a flash, ejecta, dust arcing in slow ballistic trajectories, and terrible destruction. But the sky would not carry a roar to you. The violence would unfold in silence. The Apollo astronauts gave humanity a subtle lesson in this. When they moved on the lunar surface, the moon itself was not acoustically alive around them in the way Earth is. Their microphones recorded voices, and breathing transmitted through their suits and radios. Impacts and footsteps could be heard through structure-borne vibration and suit contact, but the lunar exterior was not filled with ambient air-carrying sound. A hammer striking a tool or the ground might transmit some vibration through contact, but not bloom outward into a surrounding atmosphere. The moon is a place where motion looks loud and feels eerily quiet. That eerie quiet has psychological power. Sound is one of the ways we locate danger. We hear predators, engines, storms, collapsing trees, approaching footsteps. And silence can mean safety, but it can also mean a loss of warning. In space, the usual auditory cues vanish. You would not hear something approaching through vacuum. A tumbling piece of debris could be on a collision course, lit coldly by sunlight, making no noise at all. A spacecraft gliding past you would not whoosh. A satellite breakup nearby would not crack and boom around you. Threats become visual, not audible, until they physically interact with you or your craft. That has shaped the design of space operations and spacecraft systems. In environments where external sound cannot warn you, sensors become even more critical. Radar, cameras, pressure monitors, thermal readings, accelerometers, communication systems, computer alerts. Human hearing is powerful, but in space, it loses one of its usual domains. Technology must replace it. Silence also changes scale. On Earth, sound shrinks distance emotionally. You can hear a city before you enter it. You hear surf before you see the ocean. You hear a storm building before the first drop hits. Space gives you none of that approach music. A planet can fill half your sky in visual magnificence, while the surrounding vacuum remains dead still. A ring system can glitter around a giant world. An aurora can glow over a planetary pole. A comet can shed gas and dust in sunlight. None of it says a word to your ears. In a way, that makes the cosmos feel even larger. Silence removes one channel of familiarity. It denies us one of the senses we rely on to make environments feel inhabited. A forest is alive, in part because it rustles. A city is alive because it hums, and its space often appears visually extravagant and acoustically empty, which gives it an almost sacred distance. It is there, fully real, but unreachable in a human sensory sense. And still, if you know where to look, the silence keeps breaking in fascinating ways. Consider planetary magnetospheres. Around worlds like Earth, Jupiter, and Saturn, magnetic fields trap charged particles from the solar wind. Those particles interact with plasma and magnetic structures in ways that can generate radio emissions. Spacecraft can detect them. When these radio signals are translated into human hearing range, they produce eerie whistles, chirps, crackles, and rising tones that sound almost like something between electronic music and haunted weather. These are not sound waves traveling through vacuum to a microphone in the usual way. They are electromagnetic signals or plasma wave phenomena measured by instruments and then rendered as audio. But they correspond to real processes, and they reveal that the space around planets is active in ways our naked senses would miss entirely. Jupiter is especially spectacular in this regard. It has the most powerful planetary magnetic field in the solar system, and its surrounding space environment is turbulent and intense. Spacecraft recordings converted to audio produce some of the most unsettling and beautiful space sounds available to the public. If you did not know what you were hearing, you might think it came from a synthesizer or a horror film. In reality, it is a translation of an invisible electromagnetic drama wrapping a giant planet. Saturn has its own strange voice in this translated sense. So does Earth, and our own planet emits radio phenomena connected to lightning, auroras, and magnetospheric activity. The universe is full of signals. Human ears simply are not the default receiver. That is worth dwelling on, because it pushes us toward a more honest way of thinking about silence. Silence, in a human context, usually means absence. No voices, no music, no traffic, no wind. But in science, especially in astronomy, silence often means our senses are mismatched to the environment. Space is not inactive because it is acoustically silent. It is active in forms we are not naturally built to perceive. When we say space is silent, we are describing the limits of airborne sound and human hearing more than the limits of cosmic activity itself. The early universe gives an extraordinary example. Long before stars and galaxies formed, the young universe was a hot, dense plasma. In that early state, pressure waves really could travel through it. In a sense, the early universe had something like sound. Tiny density fluctuations moved through the primordial plasma, creating acoustic oscillations. These left imprints we can still detect today in the cosmic microwave background, the afterglow of the Big Bang, and in the large-scale distribution of galaxies. Scientists call them baryon acoustic oscillations. That is a technical phrase, but the core idea is simple enough. In the universe's hot, dense beginning, waves of compression and rarefaction moved through the matter and radiation coupled together in that early plasma. So the universe began not in silence, but in a state where sound-like pressure waves were possible. That is one of the strangest turns in the whole story. The cosmos we inhabit now is mostly too empty for ordinary sound across open distances. But in its earliest era, before expansion thinned everything out, and before atoms formed and light could travel freely, the universe was dense enough for these pressure waves to move. The silence of modern space is not timeless. It is the product of cosmic evolution. And here again, the word sound must be handled carefully. No human ear was there. The frequencies and conditions were far beyond anything like a familiar soundscape. But the physics of compressions moving through a medium was present. In that sense, the early universe was acoustically alive in a way the modern interstellar vacuum is not. This gives the topic a surprising time dimension. Space is not simply one kind of place. It changes with region, object, and era, and around planets with atmospheres, sound lives again. Inside stars, pressure waves pulse. In galaxy clusters, gigantic low-frequency waves move through hot gas. In the early universe, acoustic oscillations shaped the structure of everything that followed. Silence dominates many cosmic spaces, but the rule is not universal across all environments. Now, let us return to the phrase that bothers people most. Why no sound at all? Because sometimes someone will object and say, "But space has particles, so should there not be at least some sound?" In principle, if you had a region of gas dense enough and coherent enough, yes, pressure waves can exist. But the everyday statement refers to ordinary human-scale experiences in the near vacuum of open space. The particle density is so low that any pressure disturbance would not propagate as a meaningful, audible sound in the way you imagine. Saying space has no sound is like saying a desert has no ocean waves. On a microscopic level, there may be isolated motions, but the continuous large-scale behavior, we mean by waves, is absent under those conditions. Another useful way to frame it is this. Hearing requires not just a source and a listener, but a connected medium between them. On Earth, air invisibly connects most sound sources to your ears. In space, that connection is severed. Imagine standing in a huge cathedral. Someone drops a metal cup at the far end. You hear the ring because air fills the entire space between you. Now imagine the same cathedral magically emptied of all air. The cup still strikes stone. It still vibrates. Marple, but there is no acoustic bridge from it to you. The visual event remains. The auditory event does not. Space is that broken bridge, expanded to cosmic scale. This also helps explain why radio communication in space is not sound traveling through space. Astronauts speak into microphones. Their voices become electrical signals, then radio waves. Those radio waves travel through vacuum just fine because they are electromagnetic. On the other end, a receiver converts them back into sound inside the listener's helmet or cabin. When astronauts talk during a spacewalk, they are not hearing each other through open space. They are hearing electronics reconstructing each other's voices. The distinction is easy to miss because the experience feels seamless. The same is true for mission control, hearing a rocket crew, or for us, hearing a lander's microphone on Mars. Often, what sounds like a direct auditory connection across space is actually a chain of conversion, transmission, and reconversion. Space itself is not carrying the sound. Technology is carrying information about the sound. This reveals something subtly profound about human exploration. We do not simply go into space. We bring little islands of Earth physics with us. Pressurized cabins, breathing air, warmth, fluid circulation, sound-filled interiors. A spacecraft is not just a vehicle. It is an acoustic bubble, a tiny atmosphere in a silent void. It is a moving pocket of familiar sensory life, sailing through an environment that would otherwise erase much of what feels normal to us. That may be one reason the silence of space is so emotionally powerful in art and imagination. Now, it represents more than a missing soundtrack. It represents exposure. Without atmosphere, without the protective medium, you are stripped down to raw physical reality. Heat and cold become harsher. Radiation more immediate. Motion more unforgiving. Distance more absolute. The silence is part of that exposure. Even on Earth, silence can feel enormous. Stand in deep snow after heavy snowfall, when the air is still and the usual city noise is muffled, and the world seems altered. Stand in a desert at night, far from roads, and the quiet gains weight. Go underwater, and the soundscape transforms into something enclosed and strange. These experiences hint at how much sound shapes our sense of place. Space removes it almost entirely, replacing it with visual immensity and internal mechanical noise if you are inside a craft. That contrast can be deeply unsettling. There is another twist here, and it concerns speed. People often assume that because things move very fast in space, they should make more sound. But sound does not arise from speed alone. On Earth, a jet moving through air creates pressure disturbances, and if it exceeds the speed of sound in that medium, it produces a sonic boom. The boom is about the aircraft outrunning the pressure waves it creates in air. In vacuum, there is no air to compress, so there is no sonic boom trailing behind a spacecraft, no matter how fast it moves relative to you. A ship could flash past in silence. The laws governing the drama are different. This matters when thinking about meteors too. A meteor entering Earth's atmosphere can roar, crackle, and explode because it is interacting violently with air. The same object moving through interplanetary space before entry is not producing that atmospheric soundtrack. The noise arrives when the medium arrives. Comets provide another elegant example. Their tails look like smoke streaming behind them, and they can appear almost theatrical, as if they should hiss and roar. But those tails are made of gas and dust, illuminated by sunlight and shaped by solar radiation and the solar wind. In open space, the spectacle is visual. The drama of sound belongs mostly to the environments where gases or solids can carry vibrations to a listener. The same pattern repeats everywhere. Rings collide around Saturn, but open vacuum dominates their environment. A star ejects material in a solar flare, but the space between star and observer does not transmit that event as audible sound. A spacecraft deploys a solar panel, and unless you are connected to its structure or inside the craft hearing internal vibrations, the movement is mute. Once you start seeing the universe this way, many classic images change in your mind. Space battles become silent flashes. Lunar impacts become noiseless eruptions. Orbiting machines become moving sculptures in vacuum. Yet strangely, understanding the silence does not make space feel emptier. It makes it feel more real. It forces you to stop importing Earth into places where Earth does not belong. And when you stop doing that, the alien nature of the cosmos becomes sharper. You begin to see that sound, which feels so basic to us, is actually a local privilege of certain environments. It is not guaranteed by reality. It depends on conditions. It depends on matter arranged in the right way. Our noisy world is not the default state of the universe. It is one special kind of island. That realization can ripple backward into how you think about Earth itself. Our atmosphere, so often treated as background, suddenly looks miraculous. This thin layer of gas does so many things that we take for granted. It lets us hear one another. It carries birdsong, thunder, music, warning cries, laughter, engines, and the sea. It turns events into shared sensory experiences. Without it, the visual world would remain, but the sonic world would collapse. The next time you hear rain on a roof or leaves rattling in the wind, it is worth remembering that these are not just sounds. They are the atmosphere announcing its presence. And of course, sound is not always carried by air. Water and solid ground can transmit it too, often better in some ways. That is why whales can communicate across huge distances underwater. It is why seismic waves from earthquakes can circle the planet through rock. So if you stood on a moon with no atmosphere but placed your ear to the ground after a nearby impact, in principle vibrations could reach you through the solid surface. The silence of space is not a magical silence that erases all vibration. It is the silence of unsupported transmission across vacuum. Matter can still talk to matter if they are in contact. This becomes dramatic in spacecraft engineering. Engineers worry about vibration intensely. Rockets are unbelievably noisy during launch because dense atmospheric gases and violent engines create extreme acoustic loads, and the structure itself vibrates powerfully. Satellites and probes must survive this on the way up. Once in space, the external acoustic environment collapses, but internal vibrations from machinery, reaction wheels, pumps, and maneuvers still matter. The silence outside does not mean an absence of mechanical stress. Again, the message is not nothing happens in space. It is the pathways are different. Launch itself is almost a perfect contrast case. On the pad, a rocket is one of the loudest human-made phenomena on Earth. The exhaust slams into the atmosphere and the launch structure, creating pressure waves so intense that launch facilities use massive water deluge systems, partly to suppress acoustic energy and protect the vehicle. The roar can rattle buildings kilometers away. Then the rocket climbs, the atmosphere thins, and eventually it reaches a place where the outside environment can no longer carry that roar. The same machine, still burning and is still venting, still moving at extraordinary speed, enters a realm where its external soundtrack falls away into vacuum. There is something almost theatrical about that. A vehicle begins its journey in violence and noise, punching through the atmosphere in one of the loudest acts humanity can produce, and ends up in near-perfect external silence among the stars. Now, because this subject invites imagination, it is worth asking what a human would actually perceive during a spacewalk or in open vacuum. Inside your helmet, you would hear yourself breathing, the circulation fans in your suit, your own voice conducted through the suit atmosphere, perhaps mechanical vibrations through your body. If you touched a vibrating structure, you might hear or feel that through contact. But the surrounding void would not feed your ears. The station drifting a few meters away, Earth glowing below, perhaps another astronaut moving in perfect view, all of it would be visually overwhelming and acoustically absent, except for what your radio and suit systems recreate. That sensory combination must be extraordinary. The most majestic scene imaginable, paired with an intimate cocoon of internal sound. Your own breath would likely feel louder than the planet beneath you. Your heartbeat, if you could sense it, more immediate than the horizon of Earth. Space externalizes sight and internalizes sound. This also explains why filmmakers sometimes choose to depict realistic space scenes in silence, and when they do, the effect can be unforgettable. Without the usual cinematic audio, motion feels uncanny. Rotation becomes more disturbing. Impacts seem colder. A drifting figure or tumbling station fragment feels helpless in a way noise might soften. Realistic silence in space scenes can be more intense than any explosion sound effect because it reveals how indifferent the environment is. The lack of sound is not a missing layer, it is the message, and yet the full truth remains more nuanced than the slogan. Open vacuum is silent, but cosmic matter can still vibrate, ring, oscillate, and carry pressure waves where conditions permit. Data can be transformed into audio so that we can hear patterns we would otherwise miss. The universe can be silent and sonified at the same time, depending on what exactly we mean. Let us dig one step deeper into the environments where sound can travel in space, because this is where beginner intuition often shifts into something richer. Interstellar space, the region between stars in a galaxy, is not perfectly empty. It contains gas and dust, often called the interstellar medium, but this material is extraordinarily diffuse. In some regions, there may be only a few particles per cubic centimeter, sometimes far fewer. Compare that to Earth's atmosphere, where a cubic centimeter near sea level contains an almost incomprehensible number of molecules, on the order of tens of quintillions. The difference is not just large, it is practically total from an acoustic perspective. That is why interstellar space does not behave like a thin wind. It behaves like near nothing. Even giant nebulae, which look dense and cloud-like in telescope images, are usually far more tenuous than the best laboratory vacuums humans can create on Earth. They seem substantial because they extend across immense distances, and because their glow is captured over long exposures. If you could pass through one, the gas would be so thin you would not experience it as a fog filling your lungs or pressing on your skin. So when people imagine a spaceship drifting through a colorful nebula with thunder rolling through it, that image belongs to art, not physics. There are denser regions, of course. Molecular clouds where stars form can be much denser than average interstellar space, but still wildly rarefied by everyday standards. Pressure waves can exist in astrophysical gases under the right conditions. But the notion of standing there and hearing a roaring cloud is still misplaced. The scales, densities, and frequencies are profoundly unlike human environments. Then there is plasma, and the fourth state of matter, in which gas is so energized that electrons are stripped from atoms. Much of the visible universe is plasma. Stars, the solar wind, ionized gas in nebulae, hot gas in clusters. Plasmas can support complex waves and oscillations. Some of these are analogous to sound, others are electromagnetic or magnetohydrodynamic in nature. This is one reason space sounds can become confusing. Space physics deals with many kinds of wave behavior, not all of which map cleanly onto everyday sound, but all of which involve organized disturbances moving through matter or fields. Scientists use precise terms. Public language often compresses them into sounds, which is understandable, but sometimes too loose. The sun's corona offers a good example of apparent contradiction. The corona is the sun's outer atmosphere, extremely hot and tenuous, extending millions of kilometers into space. It is not dense like Earth's air, yet it is not pure vacuum either. Waves move through it. Shocks from solar eruptions propagate through solar plasma. Spacecraft can detect effects associated with these events. But again, that does not mean you could simply float nearby and hear a booming solar storm. The environment, the frequencies, and the medium conditions are all different from the human hearing scenario. This is why astronomy so often relies on analogy, but always with caution. Saying the sun rings like a bell can be useful if it leads to the idea of resonant oscillations. It becomes misleading if people imagine a giant, audible gong ringing through space. Saying a black hole has a sound can be useful if it refers to pressure waves in surrounding gas or data sonification. It becomes misleading if it suggests open vacuum noise reaching human ears. The challenge is to keep the wonder while protecting the meaning. And there is wonder here, plenty of it. In some ways, more than if the universe simply behaved like a louder version of Earth. The silence tells us that the cosmos is built on rules that are not centered on us. It reminds us that our senses are adapted to a very specific ecological niche, a warm, pressurized planet with liquid water, moderate gravity, and a dense atmosphere. The further we move from those conditions, the more reality stops matching instinct. That is one reason astronomy is so thrilling. It repeatedly exposes the provincial limits of common sense. Common sense says explosions are loud. Astronomy says only where a medium can carry the pressure wave. Common sense says emptiness is nothing. Astronomy says emptiness has structure, particles, fields, and deep consequences. Common sense says seeing a thing and hearing it are naturally paired. Astronomy says not in vacuum. Common sense says if something is happening on a huge scale, it must be overwhelming to the senses. Astronomy says sometimes the most colossal events in nature unfold in utter silence. There is a kind of dignity in that. The universe does not announce itself in ways chosen for our comfort. It reveals itself on its own terms. And when we do find ways to listen, those methods become acts of interpretation. Radio telescopes detect invisible wavelengths and convert them into signals. Gravitational wave observatories turn space-time ripples into measurable traces. Seismometers on planetary surfaces detect internal quakes. Plasma instruments register charged particle behavior. Microphones on Mars catch the whisper of another world's wind. Each one is a different way of extending hearing beyond hearing. Mars deserves a moment more here because it offers a rare case where the idea of sound in another world moved from theory into felt experience for the public. When Perseverance recorded the Martian wind and the sounds of its own operations, it gave people something unusually intimate. Not just images from another planet, but the texture of a place. And the texture was thin, subdued, almost shy. That is a perfect example of why sound matters emotionally. A picture shows you a landscape. A sound makes it seem inhabited by physics. Mars stopped being just a photograph and became a place with air, however little, moving around a machine built by us. Imagine what future missions might add. The dense haze of Titan, the atmosphere of Venus from a surviving probe, if technology allows, the icy creaks of a lander on Europa, if it ever reaches the surface. Each environment would not just look different. It would speak a different acoustic language, because each medium would be different. Even Earth from space offers a strange lesson. Orbiting astronauts cannot hear hurricanes raging below them through the vacuum outside. Yet those storms are among the loudest systems on the planet when experienced from within the atmosphere. So from orbit, a cyclone is a silent spiral of cloud, vast enough to cover regions larger than countries, rotating beneath you in complete visual majesty. The roar belongs to the atmosphere trapped down below. The silence belongs to the void above. The same is true for lightning. From the ground it cracks and rolls across the sky. From space, unless measured by instruments or heard via radio translation, a storm becomes a luminous flicker under cloud tops, no thunder crossing the gap to an orbiting listener. This split perspective is deeply revealing. Sound is not attached to the object. It is attached to the interaction between object, medium, and observer. By now the core answer is clear, but the subject keeps widening. Because once you understand why space has no sound, you start understanding something bigger about how knowledge works. So much of science is really the work of correcting instinct without killing wonder. The childlike version says, "There is no sound in space because space is empty." The mature version says, "There is no ordinary airborne sound across open vacuum because sound is a mechanical wave requiring a medium, and most of space is too diffuse to support meaningful propagation. Though some cosmic environments do carry pressure waves, and many cosmic signals can be sonified." The second version is more complicated. It is also more beautiful, because reality gained texture instead of losing it. And that texture matters. It is the difference between memorizing a fact and actually seeing the universe differently. When you next watch footage of a rocket stage drifting above Earth, you may notice the false sound effects many videos add for emotion. They are understandable, but you will know the deeper truth. Outside the vehicle, the scene is mute. When you see an animated supernova, you will know that the expanding shell may drive shocks through nearby gas, but the blast across interstellar space does not thunder in the way storms do here. When you hear a sonified black hole or the chirp of a gravitational wave detection, you will know whether you are hearing a real acoustic wave in matter, a translated electromagnetic signal, or a representation of space-time itself. The slogan will have unfolded into understanding. There is one final emotional dimension to the silence that is worth holding on to. Silence changes how we imagine loneliness. A city without sound would feel uncanny. A forest without birds or wind would feel wrong. Space without sound feels not just empty, but indifferent. It suggests a realm where human presence is tiny and unsupported, where survival depends on bringing your own air, your own pressure, your own warmth, your own little pocket of noise. In that sense, every crewed spacecraft is not just a machine. It is a vessel of sound carried into silence. Voices, fans, footsteps, checklists, laughter, alarms, all of it preserved inside thin walls, while the cosmos outside remains acoustically vast and unreachable. That image says something important about exploration. We do not conquer space by making it like Earth. We survive space by understanding how unlike Earth it is. And maybe that is the real payoff of this whole question. The strange reason space has no sound at all is not merely that there is nothing there. It is that sound itself is more local, more fragile, and more dependent on matter than our everyday intuition suggests. The universe is not withholding music from us out of cruelty or drama. It is showing us, with complete honesty, that the rules of reality are deeper than the habits of one planet. In that silence, there is a lesson in scale. Stars can explode without a bang reaching you. Galaxies can collide without thunder. Black holes can warp the structure of space-time, while your ears remain useless to the event. The cosmos is not built to match the sensory expectations of the creatures who evolved under a blue sky. We had to learn that. We are still learning it. At the same time, the silence is not empty of meaning. It reveals the hidden importance of mediums, of atmospheres, of plasma, of contact, of translation. It tells us why Earth sounds like Earth, why Mars sounds thin, why the Moon does not, why the Sun can ring internally while seeming silent from here, why the early universe could carry acoustic waves before the modern cosmos thinned into vast quiet. It connects the behavior of a bell in a vacuum chamber to the structure of galaxy clusters and the afterglow of the Big Bang. Few scientific facts begin so simply and end in such a wide view, and perhaps that is the most awe-inspiring part. A child can ask, why is space silent? The real answer reaches from the molecules in a room to the history of the universe itself. It reaches from your eardrum to the birth of cosmic structure. It reaches from a whisper across a table to pressure waves in stars, and to the cold near emptiness between galaxies. A simple absence opens into a map of reality. So yes, space has no sound, at least not in the open, ordinary sense your ears would expect. No roar between planets, no thunder between stars, no cinematic boom rolling through vacuum. But beyond that simple truth lies a universe far stranger than silence alone suggests. A universe where sound depends on hidden conditions, where giant structures can ring below human hearing, where data become music, where planets have accents, where stars pulse, and where the most violent events of all may unfold before you in perfect, terrible quiet. Thank you for being here and taking the journey with me. The next time you look up at the night sky, remember that above all that beauty, there is almost no sound at all. Only light crossing the dark and a silence so deep that it changes what it means to hear the universe.